Okay, in this lecture we're going to look at how we assess how good a model is. So we're going to look at three components of that question. The first being the likelihood function, so how a likelihood function is constructed and how it leads to the estimates for our model. The second is we're going to look at Akaiki's information criterion as a way of deciding between models. And finally, we're going to look at absolute measures of model fit as a way of deciding whether a model we've chosen is any good at all. So start with likelihood. The key component of the likelihood is this probability density function of x, where x is distance. And the probability density function is conventionally written as f of x. And density functions are a little bit difficult to interpret because they have rates of change of probability, actually. And so an easier thing to interpret is the density multiplied by a little bit. This little bit is dx, so that's a little distance. This is the probability density at x, and this is a little distance dx. That has the interpretation of being a probability, and in particular, the probability that the animal that we detected was between this distance x and a very close distance that's slightly larger, x plus this tiny little thing dx, from the line or from the point if it's a point transect survey, given that it was detected between distance 0 and the maximum distance w. So in a line transect survey, w would be the strip half width. Now, when distances are exact, as in when we have data in which we record the exact distance to things we detect rather than just the bin or interval in which the distance fell, the likelihood has a nice easy form, and it looks like this. So L is the likelihood, and it's made up of a product over all animals. So we've got animal number I equals 1 to animal number I equals n, where n is the total number of animals we detected. This symbol here means product of. And we've got the product over these probability density functions f of xi, where xi is the distance of the ith detected animal. So this thing here is just shorthand for this product on the right hand side here. So it just consists of working out the probability density function for the distance of the first detected animal multiplied by that for the distance of the second, multiplied multiplied by the distance, the probability density function of the distance to the last, the nth animal. And the reason that we can write the likelihood in this nice simple form of a product of individual simple terms is because we assume that these x's, the distances to detected animals, are independent. Now the likelihood function is key to estimation because the parameters of this probability density function are exactly the parameters of g of x, our detection function, and these are the parameters that we need to estimate in order to estimate detection probability, and from detection probability, abundance and density. And the way we do that is that we just find the parameter values, those are the parameters of the detection function, the values of those parameters that make this likelihood biggest. Those would be the parameters that were most likely to generate the data that we observed, x1 to xn. And we could do that mathematically, and distance does that internally. In fact, we don't maximize this likelihood. It turns out that it's easier to maximize the log of a likelihood than it is to maximize a likelihood. And that's partly because the log of a product is the sum of the logs, and it's easier maximizing things that have sums than things that have products. So we maximize this log likelihood, and the place that the log likelihood is maximum, the parameter values that maximize the log likelihood are exactly the parameter values that maximize the likelihood. So we maximize the likelihood. That gives us our maximum likelihood estimates of the detection function parameters, and maybe we do that for two detection functions, say a hazard rate and a half normal. And now we want to know which of those is better. So we're going to use Akai's information criterion, which is defined like this, to decide between those two models, decide which is the better model. Okay, and let's look at how Akaiki's information criterion is constructed. It has two bits. The first bit has this log likelihood in, and the second bit has Q, the number of parameters in. So as the fit gets better and better, the log likelihood gets higher and higher. And as the log likelihood gets higher and higher, minus twice the log likelihood gets lower and lower. So good fit leads to smaller and smaller first term. Now we can always make the fit better by adding more parameters, because that makes the function more flexible, which means it's more able to go close to the data. So as we add more parameters, this part gets bigger, and at the same time this part gets smaller. And at some point we reach the optimum where a certain number of parameters will make the sum of these two things the smallest that it can be. And that the model that leads to that is our best model. So when using ARC, we just look for the ARC, the model that has the ARC which is lowest among the models that we're considering. Now, an important thing about the ARC is it doesn't tell you anything about how good any model is. All it tells you about how good a model is, how well it fits the data compared to another model. So if you have choose a bunch of models, all of which are rubbish, you then find the model which has the lowest ARC. That just tells you it's the least rubbish model. It doesn't tell you it's any good at all. And you go ahead with the least rubbish model, you maybe get quite biased inference because your model is rubbish. So we can't just do ARC. We've got to do ARC and some measure of absolute goodness of fit. Is that model any good at all? We'll get onto that in a second. Before we do that, note a couple of things about ARC. Firstly, ARC has this nice property that models need not be special cases of one another. A model that's a special case of another model is just the other model with one or more of its parameters fixed to some number, and usually it's fixed to 0, because that takes that parameter out of consideration. Now you can't write, for example, a half-normal model as a special case of a hazard rate model, but you can still compare them using ARC, even though they're not nested. As I've said before, the way you use ARC is you choose the model with the smallest ARC. And the important point is this just gives you a measure of relative goodness of fit, not absolute. So on which point you should never pay any attention to the value of ARC. It's a meaningless number. The only thing that has any meaning is the difference between the ARC of one model and the ARC of another model. Okay, so those were some nice features about ARC, but it does have some limitations. And in particular, you can't use it to select between models when these things apply. And these things all relate to giving one model different data than another model. So if you give a subset of your data to one model and a different subset to another model, the sample size differs and you can't compare them because you've given the two models different data. If your truncation distance differs between models, you again can't compare the data, because although it may not look like it, you've actually given the two models different data, as in even if there were no detections in, say you had one model that you truncated at 1 nautical mile and another you truncated at 1.5 nautical miles, and there were no detections between 1 and 1.5. You've still told the model different things. On the first one, you've said there's nothing detected up to 1 nautical mile, and the second one you've said, well, there's nothing detected up to 1.5, and that's effectively different data. So you need to use the same truncation distance. You can't use ARC when you fitted one model to group data and another model also to group data, but with different cut points. Because with group data, the data consists of the cut points and the frequencies in the bins. And so with different cut points, you've given the two models different data. Similarly, you can't use ARC to compare models if one model has been fitted with group data and the other model has been fitted with ungrouped data. Okay, so you've fitted the models, at least two models, you've done ARC to compare them, you found which one of the models that you considered is the best model, but you still don't know whether that model is any good at all. And so now we need to assess the absolute goodness of fit. and we're going to look at a couple of ways of doing that. The first is a chi-squared test, which you may have seen in other contexts, for grouped or interval data. So in order to apply this test, you've got to have your data in intervals, and if your data were exact, then you need to create some intervals and turn your data into interval data in order to use this test. And that's not a very nice feature about the test, because you and I might put these intervals at slightly different places, and the test is not insensitive to where these intervals are. Better if you have exact data to use QQ plots and the tests that are related to that. If you have group data, you can't use QQ plots or the related tests. So let's look at the chi-squared test first. So as I said, you've got to have group data for this, and we assume here that you have U distance intervals, and you've got NI detections in interval number I, where these intervals go from 1 through to U. Then our measure of badness of fit is this statistic, and I'll go through its components briefly. So this first bit is just a sum from interval number 1 through to interval number U. And what you're summing is this term here, and it has 2 bits. The numerator is the distance between the observed number of detections in the ith interval, and this thing here is the expected number of detections in the ith interval. So you take that difference, and obviously the worse the fit, the bigger this distance is, the difference between these two, and it gets squared, and then it gets scaled by the expected number. So this is the same as this. The expected number has this n in it, where n is total sample size, so it's the sum of the number of detections in each of the intervals. And this pi thing is the proportion of the area under the estimated probability density function that lies within interval I, pi I within interval I. So the pi I is just the expected proportion of your data that lie in interval I. N is the total number of data points you have. Multiply that by the expected proportion. That gives you the expected number within the ith interval. So it's observed number minus expected number squared, scaled by expected number, and then summed over all intervals. And you can see that as the fit gets worse, the NIs are less like the expected numbers. And this thing gets bigger and bigger, and when you add them all up, you get a big number. So big number is bad fit. The question is how big does a number have to be before it's significantly bad fit, before it's very unlikely to have come from the model that you are considering? In order to answer that question, we need to know what the probability distribution of this thing is. And it turns out that if the model that you're considering, so the model from which you calculate these expected numbers, if that's correct, then this statistic has a chi-squared distribution with degrees of freedom equal to U, the number of intervals, minus Q, the number of parameters you've estimated, minus 1. And so we can use that to make probability statements about this test statistic. Okay, let's look at a real data set. So this is a Chaffinch line transect data set. And the red line is our fitted detection function. And the histogram is the observed frequencies, so the NIs. Now just looking at this, visually you'd say that the fit looks pretty good, until you get to these last 2 intervals. And then the difference between the red curve, what you expect, and the blue curve, what you observe, gets pretty big for this interval and quite big for this interval. So the badness of fit, if it's happening, is happening most down in these intervals, and we'll come back to that in the next slide. The other thing to notice briefly is that this interval here is about at 12.5, this one is about at 22.5, and so on. And the reason that I mention that is because the input you get out of the output you get out of distance from doing this chi-squared test looks like this. So it has the cells here. We've got 8 cells, as in the histogram, and it has the left hand and right hand cut points of each cell. And there's the 12.5, there's the 22.5, etc. So in cell number 1 goes from distance 0 to distance 12.5. In it, we observed 16 animals, so this is the NI 16. After fitting our model and integrating under that red curve within interval number 1, so between 0 and 12.5, we expect to get 15.32. And then we work out the chi-squared value by subtracting this from this, squaring it, dividing by this, and that gives us a 0.030. We work out those chi-squared values for each interval, and you get these numbers down here. And when we add all those intervals, all these chi-squared values for the individual intervals up, we get the test statistic, which is this number over here. Now remember, when looking at the picture, the worst fit seemed to be in the last two intervals. And you can see that from these numbers as well, because the two biggest chi-squared values are in the last two intervals. This being the biggest one, that being next biggest. So by looking at the chi-squared values, you can tell where in your distance bins the badness of fit is worst. Distance also tells us degrees of freedom. So remember, degrees of freedom is number of intervals minus number of parameters minus 1. Number of intervals is 8. This is a half normal detection function, so that's minus 1. And we subtract the other one, we get 8 minus 2, which gives us degrees of freedom 6 for this chi-squared distribution. And then distance tells us the p-value associated with this statistic when it has a chi-squared distribution with these degrees of freedom, and the p-value turns out to be about 0.6. 0.6 being very far from 0.05, which would be the point at which we would consider that our model has significantly bad fit at the 5% level. So this says that the model that we've assumed, the half normal detection function, is quite consistent with the data. So the fit is reasonably good and we needn't worry. Now these chi-squared statistic, the distribution of the statistic is approximate, and the approximation gets bad as the expected value gets low. Now there are various rules of thumb, the least conservative one being that each of these expected values should be at least 1 in order for this p-value to be valid, for the chi-squared distribution to apply. And a slightly more conservative one is that it needs to be at least 5. So if we were using the rule of thumb that we need these expected values to be at least 5 in order for the chi-squared distribution to apply, and this p-value to be approximately the correct p-value, we would worry about this interval because that expected value is just under 5. And so what we'd probably need to do is combine these last two intervals and recalculate the chi-squared values with these combined, in which case we'd have all expected values greater than 5. Okay, so that was for data that occur in intervals, or you can use it with exact data, but it's not advised because you're then losing some information by turning exact distances into frequencies in intervals. If you have exact data, then better to do QQ plots and the related tests that we'll come to in a minute. So we're going to spend a few slides describing QQ plots. And we're going to use this somewhat artificial example here to demonstrate how QQ plots work. So the histogram is a histogram of detections of 18 objects. So little n is equal to 18 here. We've seen 18 things. And the dots along the x-axis, x being the distance here, are the locations of these 18 objects. And I've highlighted 3 of them. This purple one, which is the 9th biggest detection, happens to be at 1. This, which is the 15th biggest detection, happens to be at 2. And this, which is the biggest, the 18th biggest, happens to be at 3. And we're going to focus on those just to make the point of how chi-squared tests work. Now, 9 of the observations, the total of 18 detections here in total, and 9 of them are at or below this 9th detection over here. So that's this one and these 8. And so that's demonstrated here by a histogram height of 9. 6 of them are in the second interval and 3 of them in the third interval. And so half the area under the histogram, as in half of the observations, are at 1 or less. And 9 plus 6, that's 15 out of a total of 18, which is 5/6 of the observations, are at or to the left of this 15th observation, the green one. So half the histogram is in this first, half the total histogram is in the first bin here, and 5/6 of the total is in the first or second bin. Now what we're going to do to construct the test is we're going to look at, for each of these observations, we're going to ask two questions. Say, what fraction of the data is smaller than or equal to, what fraction of the distances are smaller than or equal to this first observation? And the answer to that is 1/18th, because there are 18 observations and this is the smallest. The fraction that's equal to or smaller than the second one is 2/18ths, 3/18ths, etc., etc. So the fraction that is equal to or less than this purple observation is a half. And then for each of those, we're going to say, well, what fraction of the data would we expect to be below this, each of these points? And the way we're going to do that is we're going to work out the fraction of the area under the curve that is to the left of each of these distances. And then we plot those. So on the x-axis here, we've got the former, the fraction of the data that are to the left of each of these points. So this is plotted at, on the x-axis now not being distance. This is what fraction of the data have you gone through by the time you hit the first. Well, you've gone through 1/18th. You've gone through 2/18ths by there, 3/18ths by there, a half by there, 5/6 by here, which is where the green dot will appear, and 100% by here, which is where the blue dot will appear. For each of those, we're going to say, what fraction would we expect to have gone through? So we're now just going to focus on the colored dots for this. So by the time we hit the purple dot, we have gone through half the data. And if this was a perfect fit, then we will have gone through half of the histogram, half of the area under the fitted detection function, under the smooth curve. And so the y-axis would be half, x-axis is half, and we plot the point associated with that observation there. Then we look at the green observation. The green observation is 5/6 of the way through the data. So we plot it at that point on the x-axis. And if it was a perfect fit, then 5/6 of the area under the fitted detection function would be to the left of the green observation. And so the y-axis value would be 5/6 as well. And we'd plot the point there. Then similarly for the blue, which is 100% through, we'd plot it there. And similarly for all of the other observations, if we had a perfect fit, then every single one of them would fall on this line y equals x, the line at 45 degrees. So that would tell us we've got an absolutely perfect fit. The x and y axis here are the x-axis first, the empirical distribution function it's called, or EDF for short, and the y-axis is the fitted or estimated cumulative distribution function, or CDF for short. So this is a plot of the EDF against the CDF. Now obviously usually our data don't fall exactly on that line. And we're going to look at one particular sort of deviation from the line that's quite common as distance sampling data. And it's a deviation that happens because people round distances to 0. So these are exactly the same data as in the previous diagram of this sort, except the 8 observations to the left of the purple dot, although they occurred at various distances between 0 and the purple dot, the people doing the survey rounded those distances to 0, so they recorded all those 8 distances as exactly 0. What does the QQ plot look like in that case? Well, the purple and everything beyond it are going to be exactly where they were before, because the only difference between this and what we had previously was the rounding of these observations below the purple dot. So we're looking at the rounding of these things now. And so the fraction of the way that they are through the data remains the same. This is the 1/18th of the way through the data. That's 2/18ths of the way through the data, 3/18ths, etc. So on the x-axis, they occur in exactly the same spots. On the y-axis, how far are they through the data? Well, they all occurred 0, at distance 0, that's what they were recorded as. And distance 0 is 0% through the data. So the y-axis values for all of these 8 observations are going to be 0. So their dots are going to appear there. And then in this artificial example, we've got all dots beyond halfway through the data, so beyond this distance 1, as being recorded accurately in our model being perfect beyond the purple. So how do we assess how bad the fit is? It's clear that there's bad fit in this region here, because whenever a dot is not on the line, it's not a perfect fit, and the further it is in terms of vertical distance from the line, the worse the model is fitting at that point. So there clearly are some big distances between what we expect and what we observe. And the same question applies as previously. Well, how big is significantly big? In order to answer that question, we need to come up with a statistic and a distribution for the statistic. And we're going to look at 2 or slightly more than 2 statistics and tests. And the first is called a Kolmogorov-Smirnov test, or KS test for short. It uses only the biggest difference. So in our example, it works out the distance between the vertical distance between the 45-degree line and each of these points, and then finds the biggest one, which in this case is this one. And Kolmogorov and Smirnov worked out the probability distribution for that biggest distance, and we can then use that to calculate a p-value for this goodness of fit for this distance. The other test that we're going to look at is called a Kramer von Mises test, and the idea is similar, except instead of only using the biggest vertical distance, it uses all the vertical distances. So these ones have vertical distances of 0 because they fall exactly on the 45-degree line, and the vertical distances of these points are shown by these arrows, and instead of just using the biggest one, it uses them all. And Kramer and von Mises came up with a distribution for their statistic that uses all of these. And we can also modify the Kramer von Mises test slightly to give greater weight to certain parts of the x-axis. In particular, we might want to weight these small distances bigger because we know that lack of fit near the origin leads to poorer performance with distance sampling estimators than lack of fit far from the origin. So here's the QQ plot for those Chaffinch data that we looked at before, and looks like a pretty good fit. Most of those red dots are close to the blue line being the 45-degree line, what we expect, and where the dots would fall if we had absolutely perfect fit. So visually it looks like quite a good fit. The other thing you can see visually is you have these horizontal lines, these plateaus. So this is exactly the sort of thing we had when we had rounding to 0, except the plateau was down here at 0 and not at these other higher values. But it's a symptom of exactly the same thing. So for example, these 6 values here were probably all slightly different but quite close together. And what's happened is that the surveyors have rounded them to some exact value and the same exact value for all of the observations. So these plateaus in a QQ plot mean that there's some rounding going on, almost certainly. How good is that fit? Well, distance kicks out the KS test and Kramer von Mises weighted and unweighted. So the KS test statistic is this number here, and on its own that doesn't tell us whether it's a big number or not. But using the distribution of this statistic, which distance does internally, we get a p-value of 0.97. So that says that there's a 97% chance of getting a fit as bad or worse than you observed if the underlying model was the true model. In other words, the data is very consistent with what we assume the underlying model to be, or in other words, it's a pretty good fit. And you get similar p-values from the Kramer von Mises. So this uniform weighting is the standard Kramer von Mises, and it says the p-value is somewhere between 0.9 and 1, so again very high. And this cosine weighting gives higher weight to differences close to the origin at small distances, and it also says p-value somewhere between 0.9 and 1. So all of them say pretty good fit. So a quick summary of the QQ plot. What it does is it gives us a goodness of fit picture at high resolution being at the highest possible resolution, that of exact distances, as opposed to the chi-squared test, which is a resolution only of your intervals, your distance bins, however wide they are. So if you have exact data, better to use QQ plots and associated tests than to do chi-squared tests. The KS test and the Kramer von Mises test don't require grouping, whereas the chi-squared test does. And we can weight the Kramer von Mises to give higher weight to differences or lack of fit near the origin, so for small distances, because we know that when things go wrong close to the origin, that has more implications for bad estimation in distance sampling than when things go wrong far from the origin.